Okay, this morning I made an absolute mess of this particular lesson, and so I'm going to record this again in order for you to have an opportunity to take some better notes and get some more information than what I supplied with you in class. So what we wanted to do here is review how we draw molecules and polyatomic ions. Last year we would have called these the ugly Lewis diagrams, so that we can apply what we've learned about hybridization to determine the hybridization and then ultimately the shape of the molecule, because that's where we want to go. So again, just like last year, I just want to go over how we do this. First, we've got to add up all the valence electrons. All right, we total them all up, and if we have a negative ion, we add extra electrons, and if we have a positive ion, we subtract electrons away. To start with the structure, we place the atom with the lowest electronegativity in the middle, and it's the one that's going to be sharing all its electrons away, so it needs a low electronegativity to accomplish that. And then we make our skeleton structures with the other atoms around that central atom. Once we make our skeleton structure with single bonds, we subtract off from the total how many electrons we used in bonding, and then if we have any lone pairs, we add them starting with the most electronegative, which are the atoms on the outside. And if we have to, we move lone pairs around to make double bonds or triple bonds so that each atom is surrounded by 8 as per the octet rule, but we know that there are many exceptions to that now. Hydrogen can get away with just 2 electrons around it, beryllium can get away with 4 electrons or 2 bonds, and boron can get away with 6 electrons or 3 bonds. And you also need to keep in mind now that we have the expanded octet, and so any elements in the 3rd period or below can have more than 8 surrounding that atom. So the easiest way to do this is essentially to just go through a bunch of examples. So I will go through these right now on the Smart Notebook so that you can see how this is done. All right? So the first one here that we're looking at is CH4. All right, so we're looking at CH4, not a great color. Let's see if I can get a better color than that. And we can start with the Lewis diagram. It doesn't look like it's going to let me. Let's try. We'll go with that green. So C, H, 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 H is the Lewis diagram. Now, we didn't really need to draw or count out valence electrons for that one because we would call this what we called nice. A nice one from last year, and we could count them up, 4 electrons from the carbon and then 4 times 1 from the hydrogens. That gets us 8 electrons, and when we put in our skeleton structure, you'll notice we don't have any electrons left. We used all 8 of them up. Excuse me. And there you can see we have all of our electrons accounted for. Let's now take a look at our hybridization in here. So you can see here we've got 4 bond pairs, 0 lone pairs. That means we have 4, and therefore this is sp3 hybridized, and therefore the EPA is a tetrahedron. Tetra. All right? So essentially we don't want to get bogged down by energy level diagrams anymore or orbital views. I want now is to be able to go straight down to a 3D Lewis structure so that we can see something like this. We've got 1 hydrogen going up, 1 along there, 1 coming out front, there's our wedge, and then 1 going in behind there. H, 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 and H. All right? So that's how we would attack CH4. All right? So let's take a look at that next example. The next example of C is CO2. So we've got CO2, CO2. And again, if we were to do this properly, we would have 4 electrons, and 6 times 2, 12, and that would get us, wait a minute, what do we got here? So 16 electrons, 16 electrons. It's a funny number of electrons. Carbon in the middle, oxygen, oxygen. We've used 4 electrons. We're left with 12 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's all the electrons we have left. Now this is not a happy molecule quite yet, because carbon needs its octet filled. So we'll turn that into a double bond, and we'll turn that into a double bond. And I think we could have probably did this one right from the start because we've seen this molecule so many times. C double bond O, and there is our molecule. So let's now analyze. So again, keep in mind, we've only got 2 bond pairs because we don't count the pi bonds. And we've got 0 lone pairs, so that's 2, and therefore it is sp hybridized, and therefore the EPA is linear, right? And you have that from our little summary of hybridization. So the 3D Lewis for this one is pretty straightforward. C double bond O, and we will draw it as a line, double bond O. It is a 3D, and it's still a Lewis diagram, so we need all of our lone pairs, and that essentially is our carbon dioxide. All right? So next we have SCl4. SCl4. And you might think that this is a sulfur with 4 chlorines and that's it. But this is why we've got to add up our electrons. Sulfur has 6 electrons in the valence shell. Chlorine, 4 of them have 7. Right? So essentially, we're going to have 7 times 4, 28. 28 plus 6. So we have 34 electrons in this thing. 34 electrons. Now we're getting into some big numbers. Build the skeleton. S, Cl, Cl, Cl. All right, we'll put our Cl's in here. Cl, Cl, Cl. And you'll notice we've used 2, 4, 6, 8 electrons. 8 electrons minus 8. That gets us 26 electrons left. So let's start putting them on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and we still have 2 left, and so we must move to our central atom, which is sulfur. Now keep in mind, sulfur is in the 3rd row, and therefore it can have an expanded octet. It can have more than 8 electrons in its hybrid orbitals. And so here we've got 4 bond pairs, 1 lone pair, that's 5, and therefore we have sp3 dehybridization. And the EPA is trigonal bipyramidal. Trigonal bipyramidal, okay? So if we're going to draw a 3D Lewis structure, we need that trigonal bipyramid, right? Up and down, right? 1 coming out front, 1 going in behind, and 1 in the plane. And the question now is, when we have a structure like this, where do you put the lone pair? Well, in our structure, the angle between 2 adjacent bonds in the equator of our trigonal bipyramid is 120 degrees. So in that space, there's 120 degrees. From the polar bonds to the equator, in that space, 90 degrees. And keep in mind, lone pairs are big. Lone pairs are bigger than bond pairs because bond pairs have 2 nuclei pulling the electrons in tightly. So the lone pair is going to need to go in a position that gives it the most space. And so the nearest neighbors in the equator are 120 degrees away. And the nearest neighbors in the polar regions are all 90 degrees away. So there's actually more room in the equatorial positions for the lone pair to go. So the lone pair will always go in the equator for sp3 dehybridization. So my Cl's will then go into this position. All right? And the rest of the lone pairs on those to make the picture correct. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And actually, we really don't need to represent that bond there. So what I'm going to do now is, instead of putting the line in there, let's just put the lone pairs. All right? So that's our structure for sulfur with 4 chlorines, sulfur tetrachloride. And we had to be very careful in adding the electrons because in this case, there was a lone pair and we had to make sure we accounted for all of the electrons. Okay, let's keep rolling on our examples. Cn minus 1. So, where am I here? Back. We'll use this one. Cn minus 1. Cn minus 1. All right, so again, let's add up the electrons. 4 plus 5, and because it's a negative charge, plus 1, which is going to get me 10, oops, not degrees, 10 electrons. Okay, skeleton structure, Cn. What did we use? We used 2. We've got 8 left. Start with the most electronegative. Doesn't really matter in this case, but nitrogen is slightly more electronegative. It's more to the right side of the periodic table. 1, 2, 3, 4, 5, 6, 7, 8. We're out of electrons. Okay, but as you can see here, carbon is not happy. Carbon only has 4 electrons around it. So again, we will take a pair from the nitrogen, turn it into a bond, and we need to do this twice. A second pair from the nitrogen, turn it into a bond. And what does that get us? Cn, 1, 2, 3, 4. And we can check to see that we've got 10 electrons. 2, 4, 6, 8, 10. That is a good structure. And we'll put -1, square brackets, because it is charged. If we stop and analyze both the nitrogen and the carbon, we will find that they both have 1 bond pair, because we don't take into account the pi bonds, and 1 lone pair, 2, and therefore these things are sp hybridized, which means the EPA is linear. Those 2 bonds will separate as far as they can. And therefore the 3D Lewis is very easy, because the 3D Lewis, pardon the color, will be exactly the same as what we have, because when you draw linear, it is really easy. It's just on the plane of the page. Okay, good stuff. Now I am going quickly. We did go over this in class. I'm just putting this in here for those who are absent, and you can slow this down if you need to re-listen to it again. All right, so let's head back to a clear page. My next example is N2H5 plus 1. So we will put down N2H5 plus. So let's get the electrons. 2 times 5 plus 1 times 5. 2 times 5 plus 1 times 5. And notice we've got a positive charge, so I need to take an electron away, -1. And that gets me, looks like 15 minus 1, 14 electrons. Let's build the skeleton. Well, 2 N's means we're going to have them bonded in some way. 5 H's means I've got to distribute my H's kind of like this, 3 on one and 2 on the other. How many electrons have I used? I have used, now I've lost my little pen here. I have used 2, 4, 6, 8, 10, 12, minus 12. 2 electrons left. Only one place to put it to fill the octet. Everybody's happy, and so that's a good structure right there. And let's now analyze our N's, what the shapes are going to be. And both of them will be the same. In the one, we've got 4 bond pairs, 0 lone pairs. In the other, we've got 3 bond pairs, and we've got 1 lone pair. You'll notice they're both 4, which means they're both sp3, and their EPA is tetrahedral. So we need to draw these as 2 tetrahedrons connected together. Okay, not bad. N, and now I've got to have 1 sticking up, 1 coming out front, 1 hiding in behind, lone pair sticking up, 1 sticking out front, 1 hiding in behind, H on the end there, H on the end there, H on the end there, H on the end there. Again, this is charged, so we need to have our square brackets, and that is +1. And so those are both tetrahedral. Okay, let's see what the next one is. I'm going to have to start deleting some away. BCl3. BCl3. Let's add our electrons up. Boron. Boron is 3, and chlorine is 7 times 3. 21 plus 3, whoops, equals, don't mind that, 24 electrons. In this case, boron goes in the center. I'm not sure which one has the higher electronegativity. 2, 4, 6. Subtract 6. 18 electrons left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now you might think that we should make a double bond here with the boron, but boron is one of those special cases. It is happy with 6. So that's a good structure. We are finished that structure because boron is happy with 6. 3 bond pairs, 0 lone pairs, 3. Therefore, sp2. Therefore, the EPA is trig planar. And that means our 3D Lewis is exactly what it is. We've just already drawn it. We can put it flat on the page. Cl, 120 degrees. Oops, Cl, 120 degrees, Cl. That's an ugly looking Cl right there, so let's get rid of it. Cl. And it is a Lewis diagram, so we always need to include our lone pairs. And there's the 3D Lewis diagram for that. Okay. Oh, I still got another page left. Exciting. BRF5. So, BRF5. BRF5. So bromine. We haven't had bromine as a central atom yet, but that's the case in this case. The lowest electronegativity, that's the one we want in the middle. So 7 plus 5 times 7, right, which is essentially 6 times 7. 6 times 7, 42 electrons. 42 electrons. Okay, let's build it. Br, and now I got to have 1, 2, 3, 4, 5 bonds around it. F, 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 F. 2, 4, 6, 8, 10. We've used 10 electrons up. That leaves me with 32 electrons left. That's fun. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And I have 2 left, 31, 32. Go on the central atom. That's cool. Again, that's why we have to add up all of our valence electrons. So here we've got on the bromine 5 bond pairs and 1 lone pair, and that is 6, and therefore it is sp3d2, and the EPA is octahedron. And now we need to draw the 3D Lewis structure. Well, in an octahedron, the other day we looked at it, it's got up, down, it's got 1 in front, it's got 1 in behind, it's got 1 in front, and it's got 1 in behind. And these are all 90 degrees with respect to each other. So it doesn't matter where the lone pair goes. It actually is easier to see the shape by putting the lone pair on the bottom, because then we have our F's, F, 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 and we have our lone pairs on the F's. And in the end, we don't need this bond on the bottom here, so let's just switch it out for some lone pairs. 1, 2. And that's what that looks like there. And that's actually a square-based pyramid. On Monday, we'll talk about what the actual shapes are. The electron pair arrangement is octahedral, but this actual shape is a square-based pyramid. Okay, we've got one more to do here. Do I got another page? I do. That's fabulous. KRF6. Just to mess things up. KRF6. Oops. Change the thing. No, still no color. KRF6. Krypton, a noble gas. But if you put it under enough pressure with this fluorine, you can get it to share its 8 electrons. 7 times 6, so 8 plus 7 times 6. Yes, I'm using a calculator. I know it's sad. 50. I got 50 electrons to deal with. Krypton. 1, 2, 3, 4, 5, 6 bonds. F, 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 F. And krypton can have an expanded octet. So how many did we use? We used 12 minus 12. Minus 12. 38 electrons. 38. Let's start putting them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. 2 more. I got to put it on the central atom. 37, 38. That's crazy. Let's take a look at what we got. We've got 6 bond pairs. And we've got 1 lone pair. 7. Uh-oh, that's crazy. sp3, D3. I said you weren't going to have to deal with one of those. But that's what the theory brings us to that sp3d3. So let's not worry about what the 3D Lewis is. I'm not really that worried about it. But if we were to analyze this correctly, we would end up with sp3 dehybridization. All right, excellent. So that was the first section of this lesson for today. I am going to continue on and do another movie. I'm going to break them into 3, but I am going to stop this movie right now and let it save, and then I'll continue and do the next one so that you can get a better understanding. Because again, I rushed through the next section.